Hello, and welcome to another lecture for ME 372. In this lecture, we're going to continue on with combined loadings, and I hope you're starting to get a really good feel for them now and get pretty comfortable about summing forces and moments and drawing on the stresses that act on a stress element and getting the directions down and the equations. We have an exam coming up, and the exam will be handed out on 9/30, so a week from this Wednesday. Exam 1 will be handed out, and it will be due the following Tuesday, 10/6. So get prepared for exam 1. The large focus will be on combined loadings, and so we want to make sure you're really ready to do well on that exam. And a good way to get prepared is to make sure you can do all the example problems in the note packet and that you understand them, and that you can do all your homework and that you understand your homework. If you can do those things, you should do just fine on the exam. The exam will be closed book and closed note. There won't be any equation sheets or anything else. You will have your pencil, a calculator, and any tools to draw more circles that you need. So let's continue on with combined loadings and work through another example. This example is of a hand crank. And what we have here is a hand crank that is mounted. It consists of a single shaft that's bent. Up here you put your hand and you turn your hand around, which in turn rotates this disc and rolls up a cable that lifts this 100-pound weight. So the idea is that I come here and I apply a load here on this handle in this direction, and if I push on this handle and rotate it, it will rotate this disc and lift this 100-pound weight. And what we need to do is analyze the stresses that will develop in this shaft. So it says here, determine the location and magnitudes of the maximum stresses of the crank shown. Assume bearing A is a radial thrust bearing and bearing B is a single radial bearing. Assume that all external loads are applied at point C. So all the hand loads to lift the 100-pound weight, and these extra loads of 20 pounds in the negative X direction and 50 pounds pointing down are also applied at point C. So to talk about bearings for just a minute, a radial thrust bearing is a bearing that can handle any loads in the radial direction, and it can also carry an axial thrust load, so it can carry a load in this direction. Bearings are typically designed to carry large radial loads. This bearing here, for example, will maintain the shaft in this position by applying loads to not let it move up and down or in and out of the page. But bearings, unless they're thrust bearings, typically do not apply or have an ability to carry an axial load. So in this case, we have one thrust bearing at bearing A that will be able to carry this 20-pound load, and it'll also carry radial loads. Bearing B is simply a radial bearing and will just carry radial loads. Another important thing we need to make sure we remember about bearings is that you don't want to have a bending moment at a bearing. If we have bending moments at bearings, again, we will break shafts and wear out bearings. So when we have bearings, the summation of moments at that bearing will be 0. There can certainly be torques there, but the summation of bending moments will be 0, and we will want to design the bearings so that they have a 0 reaction moment occurring at them. Now that doesn't mean that the moment in the shaft is 0, but we want the summation of moments at that bearing to be 0. And you'll see how that becomes a little more clear as we work through this example. The dimensions here are shown in inches, so we have 10 inches from the end disc to the first bearing, 10 inches between bearings, and then 5 inches between the first bend in the handle and another 5 inches along the handle to where the loads are applied. The disc on the end has a 4-inch diameter, or 4-inch radius, and then 100 pounds pulling down that we're trying to lift. So again, the first thing that we need to do is make sure that our whole system is in equilibrium. And we do that by drawing a free body diagram, labeling a coordinate system, and then determining the reaction forces and moments. So coming to this next page, here's my free body diagram of my mechanism. Point D is the end where the disc lifts the weight. Point A is bearing A, B is bearing B, and C up here is where external loads are applied to the handle. So I need to give this a coordinate system, and I need to think about where to orient the coordinate system. And we typically want to put coordinate systems where we know the reaction forces and moments. And in this case, we know that we want a summation of moments to be equal to 0 at bearings A and B. And so those would be good locations to put our coordinate system. I'll pick bearing A because more values will be in the positive X direction than they would be if I picked bearing B. So we will locate our coordinate system here at A. X will be in this direction, Y will be going vertical as shown, and Z will be positive coming out of the page as shown here. Now we need to think about all the applied loads and the reaction loads. And I've got rid of the disc here on the end at point D by drawing the 100-pound vertical load pulling down at point D with the moment or the torque that is caused by the 100-pound load at the 4-inch radius with this 400 torque applied here shown in the positive X direction. So the disc and the 100-pound load are represented here at point D by the 100 load pulling down and the 400 inch-pound load or inch-pound torque being applied at point D. I then have this 20 applied in the X direction and the 50 applied here. So now thinking about reactions that will occur at the bearings, I know that due to this 100-pound load pushing down, I will have a force in the vertical direction at point A pushing up. And so I can draw on FAY. I know over here that due to this 50 pounds pushing down, it looks like I should have a 50 or a reaction force pushing up in the Y direction at B. So I will draw this also being pushed up. Now I look at forces in the Z direction, and I know that to generate this 400 inch-pound torque, I need to have a force up here at point C in the Z direction. And so that will be going in the negative Z direction. And so coming down here to bearing B, I will have a force in the positive Z direction, FBZ. And now I know that summation of moments about point B needs to be 0, and with this force trying to spin me about the y-axis like this, I will likely need to have a force going in the Z direction, in the negative Z direction here. However, I've chosen to list this as FAZ in this positive direction, and we'll see what happens with minus signs. So I now have all the reactions that can occur here at B. I have all the radial reactions that can occur here at A. I know that I also have the ability to carry a thrust load at A, so I'll have an FAX that will counteract this 20. So now I can come and start to sum forces and moments and see if I can get my system in equilibrium. So summing forces in the x direction, I have FAX minus 20, because this 20 is going in the negative x direction, equals 0. So FAX is equal to 20, like I would expect. And I could have easily just written this down. Now in the y direction, I have a minus 100 here. I have a plus FAY. I have a plus FBY. And I have a minus 50 here. And all that equals 0. Now in the z direction, I have an FAZ plus an FBZ minus FCZ, and all of that has to equal 0. Now I'm ready to sum my moments. And when I sum moments about point A, I'm going to have forces here at D that I'll need to account for. I'll have forces here at B, so I'll have an R cross F at B, and I'll have an R cross F at C, and I'll also have this external load of 400. So coming to summing those moments, I have the 400I plus the R cross FD plus R cross FB plus R cross FC. Now I know that point A is at a bearing, so the moment at A needs to be 0. And so I did not even include it in the equation here, because the moment at A will be equal to 0. So now I go find the details of each one of these components, and that is done here. And so summation of moments at A tells me this. Now I can group like terms. In grouping like terms, I can solve for FCZ, FBZ, and then from my summation of moment forces equation and stuff, I can get FBY as minus 16. So summarizing what I've been able to find, I can see that drawing my beam in the XY plane, I have a 166 force pushing up, a 16 pushing down. And I can actually see that when I solved for this force previously over here, I got a negative 16, meaning that this FBY is in the opposite direction that I chose it to be. And so I have a negative 16, or a 16 pushing down, and then my 50. And then I have a moment out here on the end of 90. And I draw my shear moment diagram for this member. So my shear is 100 coming down, 166 going up, 16 coming down, and then 50. My moment diagram gives me 1000 here, and then I work my way up, and I have the 90 here at the end that gets me back to 0. In the XZ plane, I have 50 coming down in the negative Z, 100 in a positive Z, and 50 in a negative Z again, and a 250 moment on the end. And this is the shear moment diagram that I get for this system. So now I need to determine the location of the critical stress in the shaft, and usually this occurs where the bending moment is the largest. And here I can see that my bending moment is 1000 at this point. So this is likely where the largest stress will occur, but at bearing B, I can also see that I have a significant moment here, and I have a significant moment in the x direction of 500 at bearing B here. So these two moments here could likely combine to be a larger moment than this 1000. In this case, that doesn't happen, and this point A becomes the critical stress location. To check to make sure my shear moment diagrams are right, I can see that my moments go to 0 at the ends, which they should go to, and I can also see that my maximum moment occurs where I cross the 0 in my shear diagram. So here I cross the 0, this is where my maximum moment occurs. Here I cross the 0, this is where my maximum moment occurs. So I feel pretty good about my shear moment diagrams, and I feel good about the location of the maximum stress. So I'm now ready to look at point A, and to do that I can cut and look at the shaft from either direction. It makes sense to look at it from the left because there's a lot less shaft and beam going on. So here is bearing A. Here are the loads that act on the shaft, and what I need to do now is make a cut here as shown, and some forces and moments that act inside the beam at point A. So summing forces, I know that I'll have a 100 pushing up because here I have 100 pushing down. Here I have a 400 inch-pound torque in the positive X, so here I'll have a 400 inch-pound torque in the negative X. And now I need to look at my moments. So coming down here, I do summation of moments at the cut. Here I'll have a moment in the beam. Having a moment in the beam is not the same as having a moment externally counteracted by the bearing. So I'll have a moment inside the shaft, plus this 400I, plus R cross FD, where this is point D. So R cross FD is given by IJK minus 10, 0, 0, and then 0, and I have the only force acting there is a minus 100 and a 0, so I get 1000 K. So the moment at the cut is given by a minus 1000 K and a minus 400 I, and I can draw those on this cut edge. Now to look at element A, which is top at the shaft, I can ask myself what stresses occur there. And I can see that the 100 will pierce through element A, so it doesn't do anything to the stresses on the top. This 400 will cause a torque, so a TC over J, and it's going around the axis in this direction, and so on the cut edge this arrow will be going up. This arrow here is given by my fingers curling around this axis on this cut edge, and I will have torque is TC over J, where the torque is 400. Now I have this 1000, and putting my thumb in the direction here and rotating around, I see that my fingers will be coming out of element A and into the bottom, so that will put element A in tension with an MC over I, where the M is 1000. And that accounts for all the loads that act on element A, and so the stresses that act on element A are relatively straightforward. We could now look at the stresses that occur on. In this example, we are going to look at a double disc grinder, where we have a grinder here and a grinder here with a single shaft going through and a motor that powers the two grinding wheels. There is 6 inches from the grinding wheel to the bearing as shown. The distance between the two bearings is also 6 inches. So from this disc to the bearing here is 6 inches. The width of the motor is 6 inches, and then from the bearing in here to the disc wheel is another 6 inches. The grinding wheels each weigh 5 pounds. So 5 pounds here and 5 pounds coming down here, and have a 4-inch radius as shown. So here we have a 4-inch radius in this disc here as shown by the center out to the edge and this 4 inches. a 20-pound radially directed load is applied at an angle of 30 degrees as shown in this figure. So right here the user is sharpening a tool and she is pushing down on the grinding wheel at an angle of 30 degrees here with the center of rotation, and she is applying a 20-pound load. So what we've been asked to do is determine the magnitude and location of the largest bending stresses that occur in the grinding wheel shaft. So we need to determine where the largest stresses occur in this shaft that goes between the two grinding wheels. So to do that, the first thing we want to do is draw a free body diagram of this grinding wheel and make sure we understand the forces that are being applied to our system. So coming over here, I'm looking at the grinding wheel from an end view. Here's my 20-pound radially directed load at an angle of 30 degrees. And associated with that is a frictional force. And the frictional force will act tangent to the disc at this point. And this angle from the vertical can also be shown to be 30 degrees if this angle here is 30 degrees. And our friction coefficient is 0.5, so 0.5 times 20 equals 10 is the frictional force. And here's my applied 20-pound force. Now what I need to do is resolve these forces into X and Y components. So breaking this 20-pound load into X and Y components results in 17.32 and 10. And breaking the frictional force into its components gives me 5 and 8.66. Now I can come here to point E and sum all the forces in the X direction and sum all the forces in the Y direction to get the net forces that act at point E on my disc. I have not shown the 5-pound weight here on this member because I'm just focusing on the forces due to the applied 20-pound load. Now I can come and draw a free body diagram of my entire system. I can see that I have 5 pounds pulling down here at point A due to the weight of the disc, 5 pounds pulling down here at point D, and then here I've drawn the 20 radial load and the frictional force in these directions. I could have also drawn those in the X and Y directions that I just computed, or actually the Y and Z directions that we just computed. So now I'm going to come to my bearing at B, and I'm going to assume that there will be a positive vertical load counteracting this 5-pound downward load. And then I'm going to assume there's also a positive vertical load at point C counteracting this 5-pound load. Now the net force here is in the negative Z direction, so I'm going to assume the reaction here is in the plus Z direction. And again, since we want zero moment, I know that the moment needs to be 0 here at point C. And if this is trying to rotate me around Y like this, then I know that this force at point B will be going in the opposite direction. So I have these assumed loads. I need to also make sure I put on here the motor torque, which will account for this frictional force up here. So summing forces in X, I don't have any along the axis. Summing forces in Y gives me a -5 here, a plus FBY, and a plus FCY, and a -5. So I can set all of that equal to 0. This minus 1.34 comes from the negative load up here at point E. So now I can sum forces in the Z direction. I'll have a minus FBZ plus FCZ minus the 22.32 that I solved for up here at point E. Summation of moments at point B I have an R cross F to get to point A. I have an R cross F to get to point C. And I have an R cross F at point E and an R cross F at point D. And then I have the motor torque here, TI. And so my summation of moments expression can be written as shown here. Going and getting all of these cross products can take some time, but the math and the numbers that I have used are shown on this page here. So summation of moments at B then results in this expression, and I can come over here and summing the forces and moments and plugging in for the unknowns and solving for them results in this free body diagram here with all the applied and reaction forces and moments. Now what I'm ready to do is come and draw a shear moment diagram for the XY plane and also a shear moment diagram for the XZ plane, and then determine where the moment is most critical. So doing that, looking at the XY plane, I will have 5 coming down, 3.6 going up, 7.68 going up, 5 coming down over here, and then I can take this point E and transfer it down here to the shaft. And so doing that, I get 5 coming down, my 3.6, 7.6, and 6.34 coming down. Now I'll look at the XZ direction, and I get these forces. And now I draw the shear moment diagram for each of these cases. And I can see where my maximum moment occurs here at point C in both cases. So that will be my critically stressed location. Since this is a circular shaft, I know that the maximum moment that will cause bending is given by the square root of the sum of the squares of those two moments, and so I'll take the 38 square it plus the 133 square it and square root it, and that will be the moment that I use to compute the bending stress in sigma equals mc over I. I can compute the angle at which that bending moment occurs by taking the arctangent of the 133.9 over the 38 and solving for that angle alpha there, and that will give me the angle at which that maximum bending moment will occur. And then I could cut the shaft and look at the reactions at the cut and draw stress elements. So this kind of sums up where we have come with combined loadings. We've gone through several examples now. Again, to be prepared for the exam, you need to make sure that you can go through and understand all the examples and also understand and work all of your homework and problems like your homework. And if you can do that, you should do just fine